Hi, this is an x86 based firewall and this is a Raspberry Pi Pico. Guess what it is? It's a BIOS postcode reader aka postcard. I'm going to talk about the LPC bus and walk through the design process. If you want to know how, please stick around. I was actually working on another project, but I found myself reading BIOS postcodes. This project consists of three parts: computer architecture, electronics, and software. Today I will cover everything divided into following subjects. During boot, the BIOS provides basic power on self-test status codes, also known as postcodes. Hardware faults can be identified by inspecting postcodes, which vary on the BIOS manufacturer. Postcards allow us to see BIOS postcodes, mostly by reading the I/O port address of 80 hex and displaying it on a 2-digit 7-segment display. Postcards are connected to PCs using various interfaces. Back in the day, postcards were connected to PC over the ISA or PCI bus. Later, the ISA bus was replaced with the low pin count bus, aka LPC bus, to reduce pins. And nowadays, Intel is replacing the LPC bus with the ESPI bus. But as it turns out, the LPC bus is not going anywhere soon. Actually, LPC bus is more common than you think. The Super I/O controller or SIO is also connected via the LPC bus or ESPI bus, allowing the CPU to interface with low bandwidth devices such as keyboard, mouse, serial and parallel ports, and floppy drive. Trusted Platform Modules aka TPM are also attached to motherboards via the LPC bus or ESPI bus, which mostly uses standard pitch header pins. For laptops or embedded devices, you most likely found an TPM IC that looks like this on the main board. TPM connectors do not have standardized pinouts, but you may find them in your motherboard manual. That being said, let's take a look at today's candidate. This is a fanless x86 based firewall that I came across in an online auction for around $8. Let's take a look inside and make sure LPC bus interface is physically accessible. We have the memory here. And we have a mini PCI Express connector. I think this is for the HDMI connector. Let's remove the motherboard and take a look at the other side of the main board. While handling motherboards, use proper ESD protection. Make sure you ground yourself before touching anything. I carefully remove the motherboard and set the enclosure aside. This is the Intel Atom E3800 series processor, and this is eMMC storage. This is the Super I/O IC. According to its datasheet, the bus type is LPC. The others are just network interface ICs. There was no chipset IC. Luckily, I found these TPM IC pads that I might use to access the LPC bus interface. Before going further, how can we be sure the I/O port address 80 hex is redirected to LPC bus? To answer that question, we need to look at the architecture. Intel first introduced the I/O controller hub aka ICH in 1999, along with the Intel 810 Northbridge. This was also the first time we had seen the LPC bus interface. In 2009, Intel introduced the Platform Controller Hub aka PCH. Some of the Northbridge functions moved to the CPU. With this, the South Northbridge paired chipset design was replaced with single chipset design. Since Intel Atom processors are popular in laptops and network devices, I should mention that the PCH has been relocated to the SoC as well as the LPC bus interface on the majority of the Intel Atom processors. SIO is connected to LPC bus in all these design types. I think it is the most common way. Now that we know the LPC bus controller is located ICH, PCH or SoC, we can find out more about LPC bus controller specifications, such as redirected I/O ports to the LPC bus and electrical characteristics. In my case, the LPC bus controller is located in the SoC. Let's check out the SoC's datasheet and look for the LPC bridge. Then let's look for postcode redirection. Now we are sure about that. Let's hope the BIOS firmware sends some postcodes. We also need to know the voltage level requirements of the LPC bus interface. As it turns out, there are two possibilities. It could be 1.8 or 3.3 volt. We can check this later by measuring to one of the bus pins. Let's check out the LPC bus specifications to find out what pins we need. The LPC bus allows different types of transactions. As you may have guessed, we are going to use I/O write cycle. To do that, we only need these signals. Electrical specifications suggest that it uses 3.3 volt signaling, but it is also mentions that lower voltage level may be used, as we already checked on the SoC's datasheet. Since we know what pins we need, let's connect LPC bus pins to header pins for ease of use. As the required pins are gathered on one side, I was going to use FPC cable, but I didn't have one to fit. So I decided to use magnet wires. Then I started to solder all pins one by one. It took me a while to align those, but it worked out nicely. For cleaning, I used a toothbrush and IPA. During the process, the enamel of some of magnet wires came off due to the use of tweezers. I used heat-resistant tape to isolate it. Yeah, well, I should have added that at the beginning. I drilled some holes in a piece of perf board to fit into the mini PCIe card slot. Then I soldered all the wires to pin headers. Alright, it is not the best setup for 33 MHz bus speed, but it is only for testing. To read I/O port 80, we need to understand how the host-initiated I/O write cycle works. Let me try to explain this in the timing diagram. The host asserts L frame for one or more clocks and drives a start value of 0 hex to the LED pins. On the next clock, the cycle type is driven by the host. In this case, it is an I/O write cycle. Then the host drives the 16-bit I/O address with the most significant nibble first.
Nibble.
Next, the host drives the data byte with the least significant nibble first. Then the host initiates the turnaround to turn the controller over the peripheral. The host will drive LED pins to high during the first clock and tri-state them during the second clock. The peripheral drives sync on the next clock, drives LED pins to low for the ready. Then the peripheral initiates the turnaround to turn the control over the host. The peripheral will drive LED pins to high during the first clock and tri-state them during the second clock. I should also mention that when the L reset is asserted, both the host and the peripheral must restate the LED pins. If the sync is not received in time or receives a resert sync value, the abort mechanism triggers. To ensure that the abort will be seen, the host keeps L frame active for at least 4 clocks. To verify what we have seen in the datasheet, let's use a logic analyzer to check the LPC bus. I am going to use this Raspberry Pi Pico based open source logic analyzer. I just connected these pins to the Raspberry Pi Pico and it was ready to go. I chose the logic analyzer, then the frequency, then the pins, and the name the pins. And most importantly, I set the trigger on the L frame pin. Then I turned on the device and hit the run button. We could catch 2 frames. Let's use the decoder to see the data on the LED pins. The host is trying to write 2 hex to the address of 80 hex. Since the sync is not received, it is aborted with the following 4 clock long L frame. On the next frame, the host is trying to write 3 hex to the address of 80 hex. Well, it all checks out. It is time for hardware. An FPGA is usually required to communicate on such high-frequency buses as 33 MHz. Luckily, Raspberry Pi Pico has 2 programmable I/O peripherals called PIO, which consist of 4 state machines each, and allow us to make fast GPIO operations without using CPU cycles. It also has a USB controller that we can use a USB serial device to get the postcodes. Plus, it's cheap. The Firewall's LPC bus operates at 1.8 volts, but the Raspberry Pi Pico GPIO is 3.3 volts. Voltage levels are not matching. RP2040 allows us to set voltage levels for the GPIOs by changing the digital I/O supply voltage. But changing that on the Raspberry Pi Pico board is quite challenging. I think I'm gonna pass that. Since we will be sniffing the LPC bus, GPIO pins will be set as inputs. I checked the input voltage for the high input when the I/O VDD is 3.3 volts. It still doesn't match the voltage level of the LPC bus on the firewall. When there is a voltage level difference between devices like this, a voltage level shifter is often used. Since the logic analyzer worked well, and this is not going to be a product, I think I will take my chances. Well, it's time for software. This is the project repo, where you can find everything about this project. I split the program into the tags to make it easier to understand. I'm going to walk through how the PIO program works. First, we pass the GPIO pins to the PIO, then initialize all pins as inputs. Then we set the shift direction for the input and output shift registers. Then we set the in pins and initialize the state machine. Let's take a look at PIO program. Get the filter setting set in the main program from the TX buffer to the OSR. And copy the OSR to Y. And clean the ISR. Then set 5 to the X for the next loop counter value. Let's get some nibbles. First, wait until L frame goes low. Then wait until L clock goes low. Then get the first nibble. And wait until L clock goes high. And repeat this 5 more times to get the cycle and address. Then copy the ISR to X and compare it to the filter we set to Y earlier. If it matches, get the 2 nibbles of data. Then 24 bits of 0 are shifted to the ISR to get the data. And finally, data is pushed to the RX buffer. In the main loop, the RX buffer is printed to the terminal. By the way, this is how to display the postcodes on the LEDs. Invert the ISR, copy to the OSR, and drive the LEDs. A few things about the system clock and timing. Since the program waits for the rising and falling edges of the clock pulses, it needs to finish the internal tasks before the next edge to synchronize with the clock. We need 3 or more cycles before and after the clock edges. That's why the system clock is set to 6 times 33 MHz. In other words, we overclocked it. Let's see the postcard in action. First, I checked out the tag, then compiled the project. Then I copied the binary to the Raspberry Pi Pico and opened the serial terminal. I found out that these LEDs display the postcode. With this, it is easy to say whether our postcard is working or not. I reset the Raspberry Pi Pico and turned on the device. We can see the postcodes on the terminal and LEDs are matching. Well, it needs to be checked on the logic analyzer, but you get the idea. Ain't it cool? I also implemented the abort frame to reset the program. For more, please check out the project repo. Please check the video description for codes, links, etc. In the next episode, I am going to share with you another project that also involves the Raspberry Pi Pico and LPC bus. Stay tuned for upcoming videos. If you found this video informative or helpful, please click like. And if you want to see more, please subscribe to help me grow my channel. Let me know what you think in comments. Thanks for watching.